Okay, so we are back with our second short video lesson for Chapter 1, Weather and Climate. Just gonna film a handful of slides here that are important and discuss them. So the environmental lapse rate is important. Average temperature decrease with an increase in height in the troposphere. So the average rate, and we use average for a reason, it can actually vary, but the average environmental lapse rate, I'm going to want you to know that, please, for your first exam in both Fahrenheit and Celsius, okay? So for every 1,000-foot increase in height in the troposphere, the temperature will cool on average 3.5 degrees Fahrenheit. How about in Celsius and kilometers? For every 1 kilometer increase in vertical height in the troposphere, the atmosphere will decrease on average 6.5 degrees Celsius. Now, you may have heard the term temperature inversion. So we expect that the temperature is going to decrease with an increase in height in the troposphere. We expect things to get colder as we climb higher and higher up to the top of Mount Everest, for example. Temperature inversions do happen. Now, the clicker to advance the slides is not working. So here and there, I will have to walk over here to the mouse. So pardon the interruption so I can advance the slides. All right. So a temperature inversion happens here or there when we get, and usually these things are quite temporary, when you have temperature actually increasing with height in the lower troposphere. Okay, so a great example of this would be wintertime when we occasionally get snow. Hey, by the way, last winter we, gosh, I don't think we got any snow. Maybe it was the winter before. I think it was, I don't know. That's a good question. Maybe we've gone a couple of winters recently that we just didn't get any snow. And not just here in Pembroke, but I mean up in Southern Pines either. Anyway, on those rare occasions that we have a snowy ground, that can actually give you a little bit of a temperature inversion, meaning that the air above, as you're moving up away from the snow, is actually warmer. We are going to scoot back over to the mouse again so that I can advance the slides. Okay. Next, we are going to talk about the layers of the atmosphere. We're going to begin with the bottom. All right, the troposphere. We might say it's the most important layer to us, something we deal with every day. It's the lowest layer. It's where we live and breathe. It's where the weather occurs. Average thickness is about 7.5 miles or 12 kilometers. But it's a little thinner at the poles and a little bit thicker in the tropics. So, by the way, something you can use to impress your friends when you're outside on a day with the thunderstorms rolling in and you're social distancing and wearing your mask and having a cocktail with your friends out on the deck, and you see a cumulonimbus cloud. The cumulonimbus cloud, well, the bottom of the cumulonimbus cloud shows the lifting condensation level, or the level in the troposphere at that moment where the air is cool enough for condensation to occur. And then the top shows where the stratosphere begins, because these cumulonimbus clouds, we'll learn more about them in a later chapter, they tend to be very tall, towering clouds, and they tend to make it all the way up to the stratosphere. So we don't have a line up there drawn in the sky showing us where the troposphere ends and the stratosphere begins. If there's a cumulonimbus cloud around, you can actually see where the stratosphere begins. Oh, and by the way, the anvil, I don't know if there's an image of an anvil in the PowerPoint or not, but you can go to Google Images and type in anvil. It's something that was used in steel making. And the cumulonimbus cloud looks like an anvil at the top. So the anvil head is pointing in the direction that the storm is headed. Moving over to the mouse again. Next, we have the stratosphere. It's the second layer up. It's above the troposphere. And it's going to reach a height, in other words, the top of the stratosphere is about at 30 miles. Now the temperature actually increases towards the top of the stratosphere, which is opposite of what you might expect it to do. I'm going to adjust the iris a little bit. I could close it a little bit. Maybe that's going to be a little bit better. Okay, so why does the temperature actually increase towards the top of the stratosphere? It's because the ozone layer is there, and basically it's an interaction of ozone molecules and the sun that can create some heat. Now, another important thing about the stratosphere, which I think we mentioned in our previous video for chapter 1, is that volcanic ash from large eruptions may make it to the stratosphere above the weather, remain there for several months, blocking incoming solar radiation, causing a temporary temperature drop. And if you're thinking that that is the answer to global warming, the answer is it's not, because we can't control when the volcanoes erupt. It's not necessarily great for everybody when they do erupt, and it doesn't cool the temperature quite enough. Okay, third layer up is the mesosphere. So, in the mesosphere, by the way, the mesosphere is the layer we know the least about, okay? Not very well studied. Why? Airplanes cannot fly that high. There's not enough air molecules to give them lift. Research balloons don't fly that high, and the lowest orbiting satellites are above it. So on that notion of airplanes not flying, there's a movie called Everest, and it's based on a true story of a few years ago there was an earthquake in Nepal, and there was an avalanche that killed some climbers. It's a good movie. It's hard to watch because there are parts of it that are very sad, but I recommend watching it just to get an idea of how dangerous it is to climb Mount Everest and why you would never really want to actually do it. And just, I mean, you just understand a little something about geology and weather. The weather on top of Mount Everest is crazy. And when I first watched that movie, you know, I didn't understand, you know, why when the storms calm down, why can they not send a helicopter up there to rescue people? And the answer is the helicopters can't fly around the top of Mount Everest, okay, because there's not enough air molecules. And that's just in the troposphere. Just so you know, Mount Everest is not quite, well, the top of Mount Everest is actually above the point where you have lost 50% of your air molecules. Anyway, so the mesosphere. Don't know a lot about it, except the temperature does what it should, which is that it decreases with height. The mesosphere can reach up to about 50 miles. We're going to move over to the mouse again and advance another slide because we're going to take a look at the thermosphere, which is the last layer, the outer layer. Okay, so thermosphere, the outer limit of the thermosphere is not well defined. Okay, so there's not a clear demarcation between where Earth's atmosphere ends and outer space begins. So temperature, again, here in the thermosphere does something weird. It increases with height because you have oxygen and nitrogen molecules, a few of them up there in the thermosphere, and they are absorbing that high energy short wavelength radiation coming from the sun. So we would say that the temperature is high, but if we still had a space shuttle, if we still had a space shuttle and if it was flying around a thermosphere and the astronauts did a spacewalk, it will not feel hot to them. Temperature is a measure of how fast molecules move. It's not really a measure of how hot or cold does it feel to our skin. So while the temperature is technically high in the thermosphere, it would feel cold because the air molecules, there's so few of them, and they're spread out far apart that you don't really feel any heat from that. So I'm going to go over to the mouse, I think one last time, and advance to one more slide for our video lesson. And maybe two more slides. Okay. So there's this other thing called the ionosphere. Ionosphere. So there's going to be ions involved here, clearly from the name. So between 50 kilometers and 250 kilometers up is the ionosphere. So you're going to see a slide where they have a diagram of this. So it covers the outer portion of the thermosphere and the heterosphere. So what happens here is that the nitrogen and oxygen molecules are easily ionized as they are absorbing that short wavelength solar radiation coming from the sun. So the ionosphere technically doesn't affect our weather, but it can interfere with satellites and power grids. And in your PowerPoint, towards the end, there's a diagram where they're showing the ionosphere, and they're showing what it has to do with radio waves. I believe the AM radio waves, maybe the FM radio waves. Some of you are like, what's a radio? Well, some of us have a radio in our car and we listen to it all the time because we don't do the earbud thing. It's not safe to drive with your earbuds on anyway, by the way, just so you know if you did not know that. Okay, I think that will do it for our video lesson. There are many slides that we skipped in this lesson, but I expect that you guys will be going into Canvas and reading them on your own and looking at all the images and graphs. Okay, this is Friday. I hope to, between tonight and tomorrow, have these uploaded to YouTube. Peace out.